Hi, everybody. This is Dr. Nigro with a Physics Fundamentals screencast. This one's going to look at forces and motion and how they relate to elevators. So elevators is an interesting case. Most of us have ridden in an elevator at some point or another in our lives, and hopefully you have recognized that you feel a little bit differently when the elevator goes up versus going down, particularly if it's moving at pretty high speeds. All right, so we need to pay attention when we're talking about these elevator problems because it's going to ask us a couple of different things. All right, so um, you need to recognize if question asks about the elevator or a person in the elevator. All right, the reason that's important is that your free body force diagram is going to look different if you're talking about the elevator versus the person inside the elevator. And when we do our problems below, I'll talk about each one of those free body force diagrams as we draw them. All right. Now, some of these problems are going to also include a person in an elevator. Wait, let me give them some arms. And that person is standing on a scale. All right. So the elevator is moving up or down. The person standing on the scale, and it asks you about the apparent weight of that person, right? And the reason they put the word apparent in here is that the weight that the scale reads for you can change depending on whether you're moving up or down. Now, we know that gravity never changes. Therefore, the force due to gravity, which is the weight, also cannot change. So what the bathroom scale is actually reading in the elevator is not your weight per se, but it's the normal force. All right. So that's what the scale tells us, not FG, which is why it's okay that it changes a little bit. All right. So whenever you're standing on a scale in an elevator, when you go up and you go down, you may find that that value adjusts as you're moving up and down. All right. So what are the options? Okay. So basically, the way I like to think about it is this apparent weight is kind of how you feel in that elevator. And I don't mean like, oops. I mean, how do you feel in terms of your weight? All right, so you really have three choices. The first choice is normal. All right, you feel just like you do if you were just standing anywhere. All right, and that happens when our normal force is equal to our gravitational force. And when that occurs, then the net force acting on you in that elevator is going to be equal to zero. And if F net is equal to zero, we know based on Newton's second law that the acceleration must also be zero. All right, so you have two choices here, not moving or you're moving but with constant velocity. All right, so if that's what's going on, your weight and what you feel in that elevator should be the same. All right. Another option is you feel heavy. All right, which means you feel like you're getting pressed into the floor of the elevator a little bit. All right. And this occurs when our normal force is greater than our gravitational force, our weight. All right. So when this happens, clearly F net cannot be zero because the two are not equal to each other. And generally speaking, this occurs when we have a increasing acceleration or our acceleration value is positive. All right. So you have a couple choices for when this can happen. All right. If you're moving up, then you are speeding up. All right. The signs of your direction and acceleration are working together. All right. You could also be moving down and slowing. All right. So if we have either of those situations, moving upwards and speeding up or moving downwards and slowing down, then you should feel heavier than you would under normal circumstances. All right. And then our last option, if you feel lighter. All right. That's going to happen when your normal force is less than your gravitational force. And again, when this happens, F net cannot be 0, and because the gravitational force is greater and it's got a negative sign, your acceleration value will also be negative. All right, so when this happens, you're either moving up and slowing, or you're moving down and speeding up. All right, now there is a fourth option. All right, that fourth option, all right, it's not a great option. It's what happens if something happens to the cable that's holding the elevator, it snaps. All right, when that happens, your normal force actually goes away completely because you're in absolute free fall, which means you should feel weightless. But hopefully that never happens. All right, so let's look at our problems. All right, so we have a 1900 kilogram elevator that's pulled up with a 20,000 Newton force. All right, we're going to start by drawing our free body diagram and writing our net equations. All right, but before we do that, I'm going to actually list out what I know. All right, so I know the mass of the elevator is 1900 kilograms. All right, and I know that the upward force is going to be due to tension and is 20,000 newtons. All right, so we'll start with our free body diagram. So we're going to have our elevator. All right, for right now, I'm going to leave my arrows equal but opposite. I know that they are not, but I'm not quite sure yet what the sign's going to be. So I've got tension pulling up and I've got gravity pulling down, and my net force is going to be equal to that tension force plus the force due to gravity. All right. All right, so let's think about this. What is that value going to be? All right, so I've got that tension force of 20,000 newtons, and I have a gravitational force, so I have a mass of 1900 kilograms, and if I multiply that by acceleration due to gravity of -10, I'm going to get negative 19,000 newtons, which means the net force acting on the elevator is going to be 1,000 newtons, and that is a positive value. So that tells me that my forces should be unbalanced. I guess I could have left Fn. Oh, not Fn, sorry. Tension. And I need to shorten my gravitational force to show that the two are not equal and opposite. All right, so the next question wants to know, what is the acceleration of the elevator? All right, so I know that F net, according to Newton's second law, is also equal to mass times acceleration. All right, so I have a net force of 1,000 newtons, and the mass of the elevator is 1900 kilograms, right? And my unknown is going to be acceleration. So I divide the 1900 over to the other side, and I find that I have an acceleration of 0.53. Sorry about that. I'm in my classroom. All right. So I have a 0.53 meters per second squared acceleration. Now, for part A, I did solve for F net more to make sure I knew my arrows were correct, but I could have done that in part B and then gone back and fixed my arrows. The bottom line is I needed the net force that was acting on my elevator to find that acceleration. All right, now let's move on to a person standing in the elevator. All right, what is the normal force acting on this person? And draw a free body force diagram as part of my answer. All right, so I'm going to start with that actually. All right, so I know that my acceleration up above was 0.53, and that is also going to be the acceleration for the person because they're standing in that elevator. All right, I have a mass for that person at 50 kilograms. All right, so I'm going to need to calculate F net. All right, and then from there, that normal force. All right, so let's start with that. F net is equal to mass times acceleration. All right, so in this case, net 50 kilograms times 0.53 meters per second squared. All right, so I plug that in. I find that my net force acting on the person is a positive 26.3 newtons. All right, so that tells me that my normal force is greater than my gravitational force. So I'm going to put an arrow in for my normal and a shorter arrow for Fg. All right, so there is my net force. Now I want to find the normal force. All right, so that means I need my Fnet equation that goes with my free body diagram, and that's going to be my normal force plus the gravitational force. So I plug in 26.3 newtons for Fnet. Normal force is my unknown, and my Fg, my force due to gravity, is 50 kilograms times negative 10, so that's negative 500 newtons. So then I move the negative 500 to the other side, and the normal force acting on this person is 526.3 newtons. Okay? All right, let's try another one. All right, here we have a 1,850 kilogram elevator accelerating down at negative 3.6 meters per second squared. A person standing on the scale in the elevator shows their apparent weight to be 5.44 newtons. All right, so this apparent weight is Fn. All right, so let's what we know. The mass of the elevator is 1,850 kilograms. The acceleration is negative 3.6 meters per second squared, and Fn is going to be equal to 544 newtons. All right, so draw the free body diagram and write the net force equation for the elevator. All right, so here's my elevator. All right, it's moving downward. It has a negative acceleration, so that means my tension force is going to be less than my gravitational force. And F net for the elevator will be equal to the sum of those two forces. All right, what is the tension of the cable? All right, so my unknown here is going to be that tension force. All right, if I look at my F net equation above, I can figure out Fg, right? Because I know the mass of the elevator and I know acceleration due to gravity, which means I need to do F net. All right, so I need to find the net force that's acting on the elevator, and that's equal to mass times acceleration. All right, you know what? I think this time I'm going to plug everything together. All right, so let me start this again. All right, the net force is equal to the mass of the elevator times its acceleration, or the force due to tension plus the force due to gravity. So this is me putting the two ways to calculate F net into one equation. All right, so the mass of the elevator is 1,850 kilograms times negative 10 meters per second squared. Oh, no, that's where we run into problems. In this particular problem, the elevator is moving at negative 3.6 meters per second squared. Do not put gravity in there. All right, don't do that. Just because I did that, don't do that. All right, now Fg, however, we're going to need gravity. All right, so it's 1,850 kilograms times negative 10 meters per second squared means that we have a value of 18,500 newtons for Fg. All right, so if I multiply 1,850 kilograms times negative 3.6 meters per second squared, all right, and then add 18,500 to that, I'm going to find that my tension force here is 11,840 newtons. So there is my tensional force. All right. Part C says draw the free body force diagram and write the net force. So this time we're going to look at the person. All right, so here's the person. All right, again, the net force acting on the person should also be negative, which tells me that my normal force will be less than my gravitational force. And the net force acting on this person is going to be equal to the sum of those two forces. All right, now this next part's a little tricky. It wants to know the mass of the person. All right, so we haven't had to do this type before. So let's look at how this is going to set up. All right, I know that I can look at Fnet in two different ways. I can say that Fnet equals the mass of the person times the acceleration, or I can say that Fnet is equal to the normal force plus the force due to gravity. I'm going to put those two equations together. So the mass of the person times the acceleration is going to be equal to my normal force plus the mass of the person times acceleration due to gravity. All right. So I plug in what I know. All right, I don't know the mass of the person, but I do know his acceleration is negative 3.6 meters per second squared. All right, the normal force was given at the beginning of the problem as 544 newtons. That is the apparent weight. And then I have the mass of the person times negative 10 meters per second squared. All right, so I only have one unknown in here, the mass of the person. So I'm going to move the mass of the person times acceleration due to gravity to the other side. So that's negative 3.6 plus 10. So I end up with the mass of the person times 6.4 meters per second squared. Let me take out that little dot there. Equals 544 newtons. All right, so the mass of the person is then going to be equal to 85 kilograms. All right, so this is another way to think about these elevator problems. All right, so in summary, all right, there are three ways to feel in an elevator. And I'm going to draw your force diagrams for these. All right, one, normal. You feel normal. All right, so that means you're standing in the elevator and your normal force and your gravitational force are equal. So Fn equals Fg. All right, when this happens, the net force is zero, which means your acceleration is equal to zero. Okay? Two, maybe you feel heavy. All right, this happens when your normal force is greater than your gravitational force. So Fn is greater than Fg. And when this happens, your acceleration value will be positive. All right, and remember, you have two choices. You're moving up and speeding up, or you're moving down and slowing. All right, and the third choice is you feel lighter. All right, this is going to happen if your normal force is less than your gravitational force. That's going to make your acceleration value negative because of the way the forces are pointing. If you're moving up, you'll be slowing, and if you're moving down, you'll be speeding. All right, and then your last option, the one that we mentioned before that we hope never happens, all right, is if something happens, the cable snaps. In that case, when you're in the elevator, you're going to feel like the only thing controlling you is gravity. All right, so you're going to be in free fall. All right, and what that means is no normal force. So basically, you'll feel like you're floating. And hopefully that never happens to you. Okay? All right, so that's just our little look at elevators and the different forces. All right, make sure again that when you work these problems, you're very careful about what the problem's asking you about in terms of whether it's the elevator or a person within the elevator. And then if you see the phrase apparent weight, that's telling you the normal force that is acting on that person in the elevator.